Hi, we are Team 19076, and here is our poster that we will be going over in the presentation. My name is Desi Steenerson, and I'm a biomedical engineer, and I will be giving you an introduction to the project as well as some information about our objective and our solution to our engineering problem. Our project was to design a rebreather that could accurately monitor and control oxygen concentration. This is a unique project because even though there are rebreathers on the market that are automated, they are often inaccurate and do not account for the effects of temperature, pressure, and humidity on the concentration of oxygen. This can be dangerous because inaccurate concentrations of oxygen can lead a person to hypoxia or oxygen toxicity. Our objective was to design a rebreather, and at first we were to design the rebreather from scratch. A week after our preliminary design review, we were given a rebreather to modify by our consultant, which changed our project drastically. The rebreather we received is pictured here, and I will highlight a few key features on the rebreather. Here is the O2 edition, and it is controlled by a solenoid that the team is not able to access. Here is the diluent edition, and it operates in such a way that at lower pressures, the diluent would be added by a manual valve based on the pressure in the system. And lastly, the O2 sensors pictured here are special sensors made by the consultant. This O2 sensor is slightly big and needs to be fully immersed in the flow of air. These O2 sensors could not be controlled by the team since the current control system could not be accessed. Our solution to these problems is to modify the current rebreather so that very few alterations would be done to the already working rebreather, and then to create a monitoring control system that would allow for accurate control of the rebreather as well as create a breathing simulator so that the rebreather could be tested. Now, one of our mechanical engineers will discuss our design and analysis.
Hi, my name is Vlad. I'm one of the mechanical engineers on the team, and I will be discussing the design and systems analysis for the project. Our modifications to the rebreather include replacing the current solenoid valve on the carbon dioxide scrubber with a new solenoid valve. A diluent addition piece, which is depicted here in the red square, was created to allow for the control of the diluent addition by the team and includes a T-bit that the regulator would connect to, as well as a solenoid valve in the small branch, and the other ends would be attached to the rebreather hoses. This is the sensor chamber that was designed with the oxygen sensors in mind because it's big enough for the oxygen sensors to be fully immersed in the flow of air. Pictured here are the modifications done to the rebreather, allowing the team to maintain the integrity of the rebreather, but also allowing the team to control the system. Lastly, here is the design to the breathing simulator, which simulates the consumption of oxygen by adding nitrogen to lower the partial pressure of oxygen. Here we have the system analysis of the project that was executed using Excel. Here are the constants that were used in the calculations. RMV here stands for respiratory minute volume, and it's the nominal breathing rate, which is set at 40 liters per minute, which was one of the system requirements for the project. The oxygen consumption rate of 1.8 standard liters per minute is the amount of oxygen that a human would consume at standard atmospheric temperatures or atmospheric conditions. But the actual oxygen consumption value used in the subsequent calculations is actually 1.96 liters per minute, which is adjusted for the measured lab pressure of about 93,000 pascals and a lab temperature of 294.8 Kelvin. Here we see the main table with the results, and we're just going to look at the first row for some sample calculations. So the first column, which is the inhale oxygen volume fraction column, corresponds to the oxygen concentration of the total gas mixture. The range is from 15% to 100% because this is one of the system requirements. The target oxygen fraction column corresponds to the actual oxygen concentration of the gas after some of the oxygen is metabolized by the human in the system. This was calculated mathematically by dividing the 1.96 liters per minute by 40 liters per minute and then subtracting that value from the original inhale oxygen volume fraction. It turns out that the amount of oxygen that is actually metabolized is about 4.9%. Moving on to the next column, the diluent nitrogen fraction is the amount of volume the nitrogen occupies for every mole of the gas mixture. This result was calculated by dividing the original inhale oxygen volume fraction by the target oxygen fraction and subtracting 1 from that value. Using this information, the diluent nitrogen volume rate was found by multiplying the diluent nitrogen fraction by the nominal breathing rate of 40 liters per minute, as previously mentioned. The average molar mass of the gas mixture for the inhalation was found rather simply by considering the molar mass of the oxygen and nitrogen and the percent composition of the mixture for both gases. The inhale mass flow rate, diluent mass flow rate, and exhale mass flow rate were all calculated using the ideal gas law in the form of the mass flow rate equals the measured pressure times the volumetric flow rate times molar mass, all divided by the gas constant times the measured temperature. And now I will give it away to Joseph, who will conclude the presentation.
My name is Joseph Allen. I'm the electrical engineer on the project, and I will now discuss how our project has changed and how we dealt with those changes. As with the other projects in the senior design program, our project was adversely affected due to the COVID-19 pandemic. The original scope of our project was to deliver a physical rebreather monitoring and control system to Paragon Space Development. However, due to the aforementioned changes as a result of the pandemic, the objective of our team shifted to delivering any and all materials that would assist Paragon in completing the rebreather system. While the deliverables may have changed, the requirements stayed in place. Frequent changes to various aspects of the project impeded our team's ability to satisfy all of their requirements. We have, however, delivered sufficient documentation that allows Paragon to understand and implement our proposed design. One of the key deliverables that will facilitate the continuation of the project is the wiring diagrams needed for proper integration of the monitoring and control system. The first wiring diagram demonstrates how to properly integrate all of the necessary sensors, microcontroller, and electronic components to allow for operation of the blower for the breathing simulator, as well as control of nitrogen addition into the system. As is annotated in this particular wiring diagram, Paragon will need to implement a 10 to 35 volt external power supply in order to meet the demands of the operating voltage of both the differential pressure sensor as well as the blower. The second wiring diagram illustrates integration of all the components that are necessary for controlling the solenoid valve used for oxygen addition into the breathing loop. External power supplies will need to be incorporated to satisfy the operating voltage of both the CO2 sensor and the absolute pressure sensor. Additionally, a 9-volt power supply will need to be integrated into the system to allow for proper actuation of the solenoid valve. Furthermore, a 16-bit analog to digital converter was added for the oxygen sensors in order to increase the precision of the readings obtained from the sensors. Thank you for listening to our presentation, and we'd like to thank our sponsor, Robert Jacoby at Paragon Space Development Corporation, as well as our mentor, Doug May. This project was done by Team 19076 with members Desi Sanderson, Joseph Allen, Kate Altman, Vlad Lisetsky, Charlie Mack, and Andrew Filiberti.